let's see, we have a cone shape, very funny shape material with different diameter. And then there's a current going in, current going out. It should be the same. You should know by now the current flowing through the whole thing is the same. The narrow end of the wire is where we say potential of 0. So here, I mean, they put it further out, but yeah, you can say here is where 0 is. So you're going to start off with some V. You take the voltmeter, you measure between the 0 and that V point, and then you go smaller, 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 smaller. This way, smaller, 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 smaller. What do you measure? That's all the graphs here. Okay, so let's go through one by one and try to logic them out of the picture. The first one, A. Same voltage and then suddenly drop. Cannot be lah. We already established that earlier. There's no such thing as voltage suddenly same throughout the whole conductor and suddenly drop. No. B would be correct if your conductor is not the shape of a cone. So if your conductor was shaped round like this, uniform area, then yeah, as you go along, you have a slower and lower potential until eventually you reach 0. So yeah, this is not correct in this case. It would be for this kind of conductor though. Then we are left with two choices. This curvy one or this curvy one. Both also curvy. How you know which one? This is where if you try out some equation stuff, you will probably get quite stuck. You're like, the equation's not telling me anything. How do I go from here? So we're going to try to think of a different way, a trick to help us understand this better. Okay, so rewind a bit. Remember I said the uniform one, right? Okay, for every section here, let's say a small section, change in length. Let's say here is x0 lah, start of the axis. For every little section that you go, you will have a drop in potential. Am I right? Okay, for small section, small drop. Then you take the same next section, also the same change in length, also the same drop. Same. So, I just write everything lah. So throughout this entire uniform metal wire, your ratio, or I should say, the change in potential over the change in that tiny length is the same. Constant. Now, where have we seen this before? Change in something over change in something. Oh, it's a gradient. So, this is also known as the gradient. The gradient here, constant, decreasing, going down. It's the same. Okay? Gradient is constant, so you have this straight line thing. But how are you going to apply the idea to this thing up here, the curvy one? So, okay, let's try this. Make sure you have chosen the answer first. You see either it's C or D. Okay, let's start off with the top. I'm going to cut this up into equal tiny lengths, the delta x, so that all my delta x is the same. Okay, give me a second. A bit not same already. Yeah. So each of these is a delta x. They're all the same. I purposely do it that way so I can see. Now let's look at the change in potential for each one of them. So the first one, you will have some change in potential for some tiny length. Okay, but then as you go to the next one, the resistance is a bit different already. What do I mean by that? Here the resistance is pretty small because the area is pretty big. Then the area gets smaller, resistance gets bigger. Then resistance gets bigger and bigger and bigger and so on and so forth. So each time your change in V will be a little larger. Then as you go on, change in V is a little larger. Then change in V get very big. Then here change in V is huge. Now this change in V is for each section. So what is happening here is, in summary, therefore, your change in V for each tiny little length is increasing. That's also known as an increasing gradient. So you have to look here. As you go from left to right, which one has an increasing gradient? This one is kind of like flattening out already, going to gradient 0. So, not D. The answer in this case will be C, because Here you start off not so steep. Then you get, wow, very, very steep. That's because of your change in V for each tiny little section. This is the fastest way to solve this kind of question. Okay? Because if you do the equation thing, you will do, then you're like, oh my goodness, miss, so many equations. And yeah, you will save a lot of time if you do this method. So yeah, think of this another way. Change in potential for each tiny little section. How is that changing? Okay, just to top up, this one here, resistance of each section is the same. Each section resistance same, but this one, each section resistance is getting bigger and bigger because the area is bigger and bigger.